Hello everyone, today we're doing one of the challenging problems, problem 54 of chapter 6, and this gives us a propylbenzene structure and asks us to determine the carbon radical formed from homolysis of the CH bond, particularly a CHA bond, so this one right here, and draw all the reasonable resonance structures for this radical. So let's go ahead and do that. So if I'm doing a homolytic cleavage, I know that it's going to be an equal split of these two electrons in the sigma bond, one to my hydrogen atom, one to my carbon. So that's going to form my radical. So I have my carbon radical here, and then my proton radical here, which is just a spectator at this point. So now it's asking for me to draw all possible and all reasonable resonant structures. So let's go ahead and draw some resonance structures. So this is one resonance structure. Another one is that we can actually form a new pi bond here with this radical donating in, and one of these pi bond electrons donating in, and then the other electron will go to this carbon here. Remember, in order to draw your resonance structures, you need to draw double-headed curly arrows. Sorry, double-headed arrows. So this indicates it's a resonance structure. Now I'm just gonna redraw my structure. So I have a new double bond here, a radical here, and then I have those two bonds still here. This is one radical, one resonance structure, but again, I can form a new sigma bond here, and using one of those electrons from the radical, one electron from my pi bond, and form a new radical over there on the carbon. And now I have this new sigma bond, this new pi bond here, my original pi bond there, this pi bond here, and now I have my radical over here. Once again, you could work your way around the entire structure, doing the same process, making a new pi bond, moving your radical over to the carbon that's directly adjacent to the far end of your original pi bond. And now I have my original pi bond here, my original pi bond here, and now I formed a new pi bond over here and a new radical here. Lastly, I can form another resonance structure with a new double bond here, double bond here, double bond here, and the radical up here. So as you see, we have 1, 2, 3, 4 resonance structures here. So B asks us, what carbon radicals is formed when homolysis occurs on a CHB bond? Draw the reasonable resonance structures. So let's draw our radical being formed from the CB bond. So remember, I'm going to get a carbon radical here. So we get a carbon radical here. And now we need to draw all resonance structures. So the only resonance structure that we can draw actually is, well, there actually is no resonance structures that we could draw, because in order to draw resonance structures with radicals, you need a pi bond that's conjugated to the system, so being one carbon apart, but there is no pi bond that's conjugated to the system, so there's only one resonance structure that I can think of for this one. So because of that, we know that what does resonance structures do? So resonance structures stabilize your intermediate. So the more resonance structures you have, the greater and more stable your intermediate will be. When something's more stable, it's going to have lower energy and more favorable. So when something's more favorable and lower energy, that's going to exist more so in nature. So this goes on to part C. So the bond dissociating energy of one of these CH bonds is considerably less than a bond dissociation of the other. Which CH bond is weaker, and explain why. So having more resonance structures means this pathway is more stable. When something's more stable, it means it's lower energy. When something is lower energy, it means that it takes less energy to break it. So it has a lower dissociation energy. So we know that when we break the HAC bond, we get 4 resonance structures that are stabilized. When we break the HBC bond, we can only get 1. So obviously in HAC, we get 4 resonance stabilization intermediates or stabilized intermediates. And that means that this pathway, breaking this HAC bond, generates more stabilized intermediates, meaning that it is a lower energy product or pathway. Because it's lower energy pathway, it's going to have more abundance in nature, and not only that, it will require a less amount of energy to break that bond. So our HAC bond is going to be weaker.